Any questions, comments?
Generally in the genome scale model, so we look only at the enzymatic reactions. So you write a reaction and link a gene to it. It will be the gene likely to transcribe to the enzyme that catalyzes the reaction, which will give in your certain phenotypes. Am I right?
That is the traditional expectation, yes. You are absolutely right, that is a traditional expectation.
So now when we are integrating our RS model, which is does not have these enzymatic reactions. It does means not all the RS reactions are based on enzymes. So can we give the GPR associations to the RS molecules? If we get what are the genes related to RS molecule?
Good question. So, this is in fact the traditional expectation is what you say is right, that is what you learn in a systems biology course. You have the genome and you can link the various genes, and therefore you can even modify the genes in silico and see the effects and so on and so forth. We looked at it differently. We looked at it as a solution of reactions, right. It does not really matter whether it has an enzymatic base or not in terms of solution of those reactions. You cannot modify or you cannot study the effect of modifying genes on that, yes, but you can study the effect of reactive species on your metabolic network, and that is what we did first, and that is what this paper is about. It has no GPRs, no GPRs related to reactive species. There are other GPRs, yes. So, that model as it exists in the paper cannot be used to study any gene modification aspects which are related to reactive species. Subsequently, we did, I mean this was the paper was sent a year plus ago. The two DDPs after that worked on GPRs. Okay. So, that particular link has a model with GPRs linked onto it. So, now it is complete, but when we started, no, and it so happened that only a part of the reactions were even relevant from a GPR point of view. Part of the reactions had enzymes mediating them. The rest were spontaneous reactions. In other words, they were not enzymatic reactions. So, it did not matter. But now it is complete. Now even that has been taken care of. Aditi, who did that, I pushed her to write a paper, somehow she did not. That was another paper. But none of us, I mean Subhashri did not have time to, it takes a lot of time to write a paper. Aditi could have done it very easily, but she did not have the time after she graduated. So, that is why it did not go out as a paper. I said fine, let us at least put out the GPR integrated model for all to use. It is there, it is certainly there. If you want to use it, feel free. So, that is a complete thing. So, it is actually a regular genome scale metabolic model with all the possibilities that go with it being available here now, but the one in the paper is not.
So these genes will also include genes which do not code for an enzyme. Since if some loss is reacting with a protein, which is not an enzyme, and it is still giving its effects. So are those also
Those need to be included as reactions, separate reactions. If they are not enzymes and you want, there are many such things. There are many such things. All the relevant reactive species reactions that were known are included there, certainly. Of course, it is not complete. There could be reactions that we may not know. It has about 342 extra reactions. Even to get that was quite a bit of quite a lot of struggle. So many years of struggle. Okay. So it's far better, and only thing is that it's scalable. As and when things come, you add in the same framework. You can add, no problem.
another doubt was the nomenclature part. So we integrate the
Nomenclature is a pain. Nomenclature is a pain, and that's the reason why we say it is in principle integrated. You'll have to go through your Excel file and change your nomenclature to fit your genome scale model. Okay. She has done a course on systems biology, so she's getting into all the problems that we faced. Okay. If you haven't done a course, you will not know anything about this. So don't worry. Yes, nomenclature is a big pain, but Subhashri has handled it. Now she knows exactly what to do. So she goes, change this column, just compare this column, this column through a program, and then you go and check. All that she does. Now it can be done. Now we can be more confident in saying that easily integrated with any model. And then she created something that can be done for microbes, or not she. She oversaw that work. The work was actually done by Raja and others. They created something that can be done for microbes also. That's also there. Pardon?
I was about to
Ask.
that.
See, what happens is the microbes, in fact, very interesting things we had to consider. Um, the reactive species don't cross the membrane because they are charged. Okay, so that we had to take care of through some means, and then so the transport part of it needed to be handled differently. There are in the case of a bacterial, that is in general. In the case of a bacterial system, you don't have intercellular compartments, so that had to be handled separately. Essentially, put everything else, everything in the cytoplasm. Most of the things in the cytoplasm. That is. So those were the things that were done, but now it is all done. They all exist. So that's why it took a lot of time.
I'm still not clear about the genes which do not call for an enzyme. Like if it's a binding protein or something of that sort to which the ROS is reacting. That can, as a reaction, yes, it can be included in the model.
And already included. Already included if it is known. If it is known, we could find it in the literature, it is included.
How would you frame that reaction? Like RS plus that protein giving a
Yeah.
modified protein.
Protein.
Because there is no metabolite. See, I'm just talking about.
There is no non-protein, the protein is the metabolite. In other words, it's not an enzyme anymore. You don't have a GPR for it, but you treat it, anything can be treated as a metabolite. So that was the, if you want to call elegance of that system. Anything can be treated as a metabolite. Yes, you're solving a set of reaction equations. That's it. Yeah, that's why I was kicked about this idea. The brute force idea, but it takes care of all these things. I didn't quite like it the way I've liked my other ideas, but it works. It works well. And in the current status of information, is the only thing that makes any sense. But people in the community were excited about the idea, because when Subhashri presented, they asked her, "How did you get this idea?" So that's when I realized, oh, good, it is, because when ideas come, you don't realize that it is great and all that. Okay, so it was something that occurred to you. Why not do this? So you did this. And then when such questions were asked, then she said, no, it was my advisor's idea. He's been working in this area for 30 years and 25 years plus. And so they were fine. Otherwise, Paulson asked her this. How did you come up with this idea?
Okay.
Which is good. Any other questions? Comments?
About the effect of pH, one of the preliminary work done, and the effect of pH and temperature on the kinetics. How do you integrate that into when making the model?
No. What I meant was, you would have data, but you would have data at a non-physiological pH. That you really cannot use, very strictly speaking, somewhat strictly speaking. That is what I meant. Then we tried using some models, but then we were not too sure, so we stuck to data that we knew. That's it, as comprehensively as possible. In other words, more searches needed to be made to get to that data. There are models. There are some good. Arrhenius thing will take care of temperature. Arrhenius expression will take care of temperature. pH you can to a reasonable extent, but it's not widely done. You can do.
These details are used to generate the constraints. That's what we'll have to apply constraints for the RS data, which will
No.
for their either if it's a basal model or a Hansen model. The
The constraints were not used this way. No. See the whatever you say, it's a physiological system. It has to operate at around its normal temperature and normal pH. So that was not a problem. As long as you knew what is happening at that and whether it was happening at that pH and temperature, you are fine. Okay. So those were not used as constraints. The constraints were essentially the flux limits that were used to figure out whether a reaction happens or doesn't happen. So we had to, in terms of the transport and so on and so forth, we had to cut off by using those as zeros. That's what we did. Anything more, it's beyond my comfort zone in terms of the actual doing. That's why I say they did the whole thing. Talk to Subhashri, she'll tell. Send her an email, she'll tell. Any other questions, comments? Good. I'm glad.
You say when you submit the papers to journals, they don't like that. What does it mean? They reject because.
Yeah. Yeah. See, I'll give you an example. Between 2009 and 2013, not 2009. When did we realize this? Around 2010 or something like that, first, okay, this will be the last thing. The first doubts of the relationship between the levels of reactive species and its corresponding enzyme. For example, superoxide and superoxide dismutase, we accepted 2010 or something like that. After a lot of experiments, initial experiments, they said we are trying to find out. Initially, it was just an exercise. Kavya came back and said, I don't find any correlation. I said, how can it be? You've done something wrong. Repeat, repeat, repeat. No, very, very consistent, no relationship. So by 2010, I was convinced. And then it seemed big, so we did it on different systems, different domains, bacteria, eukaryotes and so on and so forth. Algae we had done. Algae, of course, is a eukaryote. So across domains we did and built up that, and its consequences were significant. Therefore, I wrote the paper. Okay, I didn't even ask the other students to write the paper. All were authors, brought in various pieces of data from various different systems, collected over 6 years, wrote the paper, sent it to Nature, Science, everything. Everything was a desk reject. Okay. It was not even sent out for review. And then after running through the top line of things, I didn't want to publish it somewhere. So then I waited, and Uma's paper, I added this onto Uma's paper, at least the cancer part of it, and sent it and put the other data in the supplementary figures. That's how I got it published. Okay. A couple of months ago, when Sonal presented her work, I think all of you were there. There was a lot of discussion on that one point. It was not even her work. Okay. This was 12 years after the work was done. And this is normal. So, this guy, there's a saying, right? I think I mentioned this earlier also, fools and madmen. Aldous Huxley. People are so, did I read it out in this class? I didn't even remember I forgot the Huxley name at that time. I'll read out this, and then we'll stop at that. We are out of time, way out of time. We are meeting on Friday, which will be an overview class, and then we start the presentations. Okay, Huxley quote. A vast majority of human beings dislike and even actually dread all notions with which they are not familiar, and science is no exception. Okay. I have learned this again and again, because our work tends to be that way, or was that way. Now I have shifted. Hence, it comes about that at their first appearance, innovators have generally been persecuted and always derided as fools and madmen. That's what it is. With that we stop, we meet on Friday. See, nice, I mean nice discussion, although with one person. But that's okay, that's fine, that's perfectly.
This is how she scored
Uh-huh.
in the quiz.
Pardon?
This is how she scored a lot of on the last week.
Yeah, all of you did well. All of you became comfortable. So you knew how to read and then go back and read, and all that, if you look back, are designed so that you learn better. That's it. I think it's all open notes anyway. So. Wait.
One thing I would like to mention is this whole exercise of link centers. They've increased the speed in which I read research articles.
Good, very good. As long as you shouldn't spend too much time. See, you should. I hope that you were exposed to how to read a paper. You're not supposed to start from the beginning and read till the end. You're supposed to process it. So you start with an abstract, of course, the introduction, conclusion, then results and discussion, overview. If you're interested, read the details. Materials and methods only if you want to reproduce the thing. Okay, and of course to know how they were measured and all that you need to. That's all. So you should not start from the beginning and end. You won't understand most of the things anyway, because it is usually way off from what your comfort zone is. But you need to understand that you pick it up and then revisit the paper as and when needed to pick up all these other things. That's it.